Central Time. I'm your host, Dr. Matthew Richardson, and welcome to another stream of CosmoQuest Astro Office Hours. Hey guys, got started late here. Give me a second to just quickly set up and then verify that everything's going okay with the stream, and we'll go ahead and get into today's problem. Better yet, let me switch that around. Well, if you guys can see me, that is, let me get rid of the black space first. So that's really easy to do. Let's just do this. Make another window. This one I just call PDF. All right. Let's put that one all the way back up top. All right, correct the window size. I want it right about there, actually. I think this is good. All right. Increase the font size, and then let's now go ahead and make sure that the stream is actually streaming. So I'm going to go ahead and navigate over to Twitch through Chrome. Let's see. All right. Things appear to be functioning properly. And I think we're good. Hey, Guido. All right. Let's go ahead and get into it. So, I believe this would be the third stream that's related to this particular topic that we're talking about here. The reason why we were doing the stream in the first place is because one of the viewers, Larry, wanted to know if Newton's law of gravitation holds when one of the masses or both of the masses are moving relativistically. Short answer to that question is no, it doesn't hold. And the reason why it doesn't hold is based off of what general relativity tells us. And so we decided to go ahead and see if we could kind of get an answer to this question by not answering the question directly, but using general relativity to derive Newton's equation for gravitation. So in doing this, we're not exactly going to be calculating, well, what is the gravitational force between two masses if one of them is moving relativistically. We're kind of getting the idea of how you go about approaching solving that particular problem using a more simplistic problem, but related nevertheless. All right. So what I need to do here is, and I started down one approach, one path of solving this, and then quickly came to the realization that I don't want to take that path. A lot more math was involved, and so I'm going to go ahead and quickly walk through what we've done so far, and then we'll go ahead and we'll start down the path that will get us to the same destination. It's just that it's an easier path, mathematically speaking. All right. So what was the problem we came up with was, what is the Newtonian gravitational potential at a distance r due to a particle at rest in space according to general relativity, which is, of course, going to be related to Newton's law of gravitation. That is the more popular form, which is going to be the force of gravity between two masses is equal to the gravitational constant times the product of the masses divided by the distance between them squared. And so when approaching this problem, from the perspective of general relativity, we need to apply a few conditions. These conditions are generally known as the weak field approximation conditions, but the conditions are, as stated here on the page. Let me make sure that you guys can see that just fine. So I'm going to zoom in a little bit more. So 1, particles must be moving slowly. So in our case, I've just made it simple that the particle is at rest. 2, the gravitational field from the particle must be weak. In other words, you can't have a very massive particle, or you can't have a particle that's moving very fast, approaching the speed of light. And 3, the gravitational field cannot change with time. All right, those are the 3 conditions we have to apply for this problem. And so Einstein field equations are best summarized in the equation we now see here. So this is actually a tensor equation, and because it's and if you've never worked with tensors before, the way in which you can think about this particular equation is that it's a matrix, a 4x4 matrix that has 16 elements in total. However, only 10 of those elements are unique. And so, just to break down the equation really quickly, you get G sub mu nu, which is going to be the Einstein tensor. R sub mu nu is going to be the Reciept curvature tensor. R is the scalar curvature value, and essentially this is going to be the sum of the diagonal elements of the Reciept curvature tensor multiplied by the respective diagonal elements of the metric. G sub mu nu is going to be the metric tensor, and that's everything for the middle portion of this equation. And at the far right hand side, we have basically a constant that's composed of 8 pi g, g being Newton's gravitational constant, c being the speed of light. And then lastly, we have one more tensor, which is going to be the stress energy tensor, represented by T sub mu nu. And so really what this equation is telling us is that the middle portion of this equation is telling us that we have our curvature of space-time, and that curvature of space-time is related to the right-hand portion of our equation, which is all related to what's going on with the mass within our space-time. All right. So quickly moving on, and we've talked about this stuff before. The stress energy tensor, as stated before, it's this is going to be a 4x4 matrix. And again, just to not go into too much detail, it gives you information about what's going on with the mass in your system. Where in the case of our problem, only one element of this tensor is important, and that's going to be the 0, 0 component, which is basically going to be the mass density of our system. In this case, we're only taking one particle, so it's just going to be the mass of that particle divided by the volume it takes up. Okay. Moving along. Make sure I'm keeping up with comments here too. Hey, Larry. And may the 4th be with you as well, Peter. You're the second person who said that to me today. All right, and so we end up starting off with looking at the left-hand side of the equation, which in this case is going to be the middle equation we saw earlier with like the Reciept curvature tensor and everything. And so we started the problem off by establishing the metric tensor, which basically is going to allow us to define the coefficients of an equation that will allow us to determine the distance between 2 points or 2 events within our space-time. And so the way in which we define our metric tensor was that we can start off with the fact that if you could imagine a flat sheet, this flat sheet would represent our space-time. Without the presence of mass, our flat sheet is just a flat sheet, right? Well, think of a bed sheet, and you and someone else is holding the bed sheet. Our flat sheet remains flat. That is our space-time. But the moment you start adding mass, let's say, for example, you put like a rock on our flat sheet, it's going to cause the sheet to dip. The sheet's no longer flat. It's now has curvature to it. It's no longer a flat space-time. It's now a space-time that's flat plus some bit of curvature to it. And so you can account for, points along your flat sheet where there's like these dips by adding on, as long as the dips are small, you can add on to your flat space-time equation a perturbation or something that represents that change. And so that's exactly what we did here. We took our metric tensor, which we've defined as G sub mu nu, and we've said it's going to be equal to our flat space-time metric, which in this case is going to be represented by eta sub mu nu, which is basically the thing that looks like an n sub mu nu, plus these perturbations that are being brought up by the fact that we now have mass within our space-time, and that mass is actually it's affecting our space-time. But we have the condition, of course, that these perturbations to our flat space-time, this h sub mu nu, is such that it's really, really small. And so, given these conditions, we end up getting G sub mu nu, our matrix, which is a diagonal matrix. Again, all the matrices that we work with will be 4x4 matrices, and the reason why that is because you can imagine each row or each column corresponding to a coordinate in our space-time. And so our space-time, of course, is going to be composed of 3 spatial coordinates. If you want, you can think of it in terms of x, y, and z, a Cartesian coordinate system, plus a temporal coordinate, t. All right. And so we talked about this, and we also talked about the fact that you have to worry about the fact that the metric has 2 forms. One form is going to be if I'm not mistaken, this is going to be the covariant form of the metric, which is represented by G sub mu nu. And then you have the contravariant form of the metric, which I'm going to scroll down and is given here. All right, so again, we're talking strictly about the curvature space-time component of the Einstein field equations. And so one thing that we end up noting was that because of the fact that the stress energy tensors component, the only non-zero component is the 0,0 component. We only really have to worry about the Reciept curvature, the 0,0 component of the Reciept curvature tensor as well. And so we went ahead and we started to solve that. And to make it very short, it looks simplified. It's very simplified here. But these 4 terms actually expand out to being a lot more terms. And so, given some conditions that we are enforcing, and that is that the field is static, that is, it's not changing with time, which was our 3rd condition for this problem. All time derivatives are going to be equal to 0. And so the temporal coordinate in this case is the coordinate that corresponds to 0. So this partial sub 0 represents partial derivatives with respect to time. And so we can ignore those particular terms. And what else? There's one more thing that we can ignore, but I'm going to bring that up a little bit later. So as we see, we kind of got 4 terms here, and these 4 terms expand because due to the notation that's being used here, which is going to be summation notation, these terms expand out based off of sums. So the first term is a sum composed of 4 components. The second term is a sum composed of 4 components, and the same can be said for the third and fourth term that we're seeing here. Okay. So I went ahead and started working out these individual terms. And before I even get to that, I should make a mention about the fact that within these terms, we have partial derivatives, and also we have these things called Christoffel symbols, which are essentially combinations of using our metric and partial derivatives. So based off of what we're seeing here, we're actually going to be able to get both second order and first order partial differential equations. All right, first term, went ahead and solved it, ended up getting this solution. And then, of course, went through all the other terms, solved those, got their solutions as well. And finally, we end up with the overall solution for the 0, 0 component of the Reciept curvature tensor, which is going to be shown here. Fun math. Just got to be careful with all the signs and stuff like that. Okay. So this is where I want to get to. So the path that I was starting down was attempting to solve the equation as is. And that is, if I scroll back up to the very top, I was attempting to solve the equation in this form that we see here. R sub mu nu minus 1/2 R G sub mu nu is equal to a pi G divided by C to the 4th power times the stress energy tensor. However, there's a lot more math involved if you try to solve it in this form. So I've decided to not solve it in this form and to use another form to solve this problem. And instead of actually deriving what that form is, I'm just going to simply, just state it here in the document. So let's scroll back down. Let's go back up here. And what I'm going to do here is I'm going to, simply because that path was not nice. I wasn't liking it at all. So I'm pretty sure if I didn't like it, you guys were not going to like it as well. A lot more math involved. So what we're going to do here is we're going to still solve for the scalar curvature. But we're going to solve for it, or we're going to state it though, in terms of the stress energy tensor. And so, not to say that the current equation is not right. It is right. It's just there's another form of the scalar curvature. This particular form is in terms of the Reciept curvature tensor, but instead we can write this in terms of the scalar curvature tensor. I mean, in terms of the stress energy tensor. Excuse me. And so what we end up getting now is that this can be written as, if I'm not mistaken, it's kappa T. I think it's, so I'm just going to quickly change this. And so what we can write this as is that the scalar curvature R is equivalent to kappa, which in this case, kappa represents the constant that was shown on the right hand side of the equation earlier. It's the 8 pi G over C to the 4th power. And so kappa is and it's just amazing how you can make little small changes like this, and it makes the problem so much more bearable. So that is our kappa. And and it turns out that T there is it's basically the trace, or it's basically the sum of the diagonal elements of the stress energy tensor multiplied by the corresponding diagonal elements of the metric. And so what we end up getting from that is that R reduces to being negative kappa times T sub 0, 0. And let's format that so that it looks better than what it is right now. All right, that's better. All right. Okay. So, but more generally though, if I really wanted to write this in the most general form, I think the way in which I could write it more generally is, and I'll just put this at the very top, R is equal to, and again we can use kappa, and I think it's going to end up being the metric, the contravariant form of the metric, G superscript mu nu times T subscript mu nu. And again, I need to put that character turn in there. All right, there we go. Okay. I think this is right. It's been a while. I think this is right though. All right. So yeah. Okay. Better yet, what I'm going to do is instead, I'm not. I think this form of the scalar curvature is good. All right, we'll continue, and if there's any issues though with this, then I'll quickly notice it and I'll make the correction. All right, so what we can do now is we can now write the new form of what the Einstein field equations can look like. And so again, I'm just going to go ahead and put no indent. Einstein field equations. And so now we end up getting, and that's because of the fact that we've been able to rewrite what the scalar curvature is in terms of the stress energy tensor. For a second there, I thought there was a problem. But it looks like there's a problem, but hopefully the problem resolves itself. That is, with Keeper of Maps connection. What's up, Big J? Hello, Astro. Hi, Susie. And I think I said, if I didn't say hi to you, Peter, I apologize, and hi, Peter. All right, let's continue, guys. So so this other form that we can rewrite the Einstein field equations in terms of is that we'll now get that R sub mu nu is going to be equal to it's already kappa. It's going to be kappa so T sub mu nu on the outside and this is going to be a minus a 1/2 All right, I'm totally not remembering it. I'm just going to look it up. I don't use these equations very often, so I'm just going to look it up. It's going to make it easier. That way I know I don't get it wrong. So, and I'm pretty sure this is something that can be easily seen on like Wikipedia. Let's see. But basically the way in which you can get this different form of the equation is by doing, I believe it's called a double contraction. Let's see if they have the other form of it. Okay, it's not here. Somewhere online. Oh wait, nope, I'm wrong. It's here. It's just that it looks weird. So let's actually go back. How do I define that? That looks right. I'm quickly looking at how I define the scalar curvature in terms of the stress energy tensor, and I think that's good. I think that's good. All right, but the other form that you can rewrite this in terms of is going to be given by all right. It's going to be given by, we can move the kappa outside actually. Oh man, I really want to be able to state this all in terms of T sub mu nu on the outside. Let's see how I can do that. Well, I'll use the form that's here. So basically, we'd have our kappa, but I'm just going to go ahead and write out what the kappa is. So we get 8 pi times g divided by c to the 4th power. and this is going to be multiplied times. And again, this is all on Wikipedia. Unfortunately, they don't have equation numbers, but it is in the section entitled Equivalent Formulations on the Einstein Field Equations Wikipedia page. And so we can go ahead and write out T sub mu nu inside. All right, mu nu minus a fraction of 1/2 times T times G sub mu nu. And I think that that's that. Oh, what did I do here? Oh, the G for the 8 pi. Let's correct that. And I think that that should be good to go. And so this is the it's still the Einstein field equations, just shown differently. And kind of really what I've done is I've taken the term that had the scalar curvature in the previous Einstein field equations I showed you, and just moved it over to the right hand side of the equation. But of course, in doing so, I need to now restate the curvature, the scalar curvature, in terms of the stress energy tensor. All right. So this so far so good. All right. So now that we have it in this form, we should already note that the component that we're going to be solving for, of course, is still the 0, component, because all other components of the stress energy tensor were 0 anyway. So we're only concerned with that component. So what we can do now is we can note that I'm going to actually erase. Right. I'm going to go ahead and erase some of this because it was a part of the other approach that I was doing, and like I said, I just didn't like where it was going. And so now what we can do is so no indent. We can still go ahead and we can equate now that the 0, component of the Reciept curvature tensor and guys, note, this is supposed to be the simpler approach to the solution. All of this math is for the simpler approach. But we knew that we were only concerned with the 0, component of the Reciept curvature tensor due to the fact that there's only the 0, component of the stress energy tensor. So R sub 0, we got our constant, and inside that parentheses we're going to have T sub 0, and this is where we're at so far. But this, of course, is going to still require, though, that we find out what that T is, right? Which is, I guess for another way, if you can put it, is it's the scalar term or the scalar value of our stress energy tensor. Just like R is like the scalar value of the Reciept curvature tensor. And so to solve for T, so solving for T, we end up getting the following. Okay. Trying to make sure that everything can be viewed still. Begin or end align, excuse me. And so T takes on essentially the exact same form as R, but for the stress energy tensor. So T is going to be equal to I think it's the contravariant. I always keep getting those mixed, contravariant versus covariant, but I think it's the contravariant form of the metric. So G superscript mu nu times the covariant form of our stress energy tensor. So T underscore mu nu. But again, guys, we've defined the stress energy tensor, the covariant form, and the covariant form only has one component. And not interestingly enough, but also the contravariant form would also only have one component. So what this ends up coming out to be equal to there. And remember, guys, I don't know if I stated it for this particular stream, but in past streams, I stated that whenever you repeat an index or indices, you always sum over them. In this case, this sum becomes this. So equals, and I'm just going to copy and paste because it's going to make it easier to get the terms. There'll be 4 of them. The first one's going to be the 0, 0 component. The next one's going to be the 1, 1 component. 2, 2. 3, 3. And so this is exactly how it would expand. But the thing about it is that the stress energy tensor, again, and I think I'm pretty sure I've said this before, it only has one component, only the 0, 0 component. Everything else is 0. So it just simply reduces just being, I'll quickly write this out. G sub 0, or G superscript 0, 0 times T sub 0, 0. And given the fact that the G superscript 0, 0 is going to be, if I'm not mistaken, it's -1 minus our perturbation for that particular component. And that perturbation is going to be very small, and it can be ignored. This essentially reduces to being, T sub 0, 0. Which is simply going to be equal to the mass density of our system, rho. And so with this, we can now go ahead and we can solve for the right-hand side of our equation. So what I'll do is I'll go back. I'll just simply copy and paste. It'll make it, so Einstein field equations. And we end up getting that R sub 0, 0 is going to be equal to and I'll make my substitutions now actually. So rho 1/2, this is going to be a rho as well. Or negative rho, sorry. That's where I made the mistake. So this should be negative Should be a negative rho. Oh no. Okay. What line is this? Line 175. It's not happy about something. What did I do? I have a left. It's definitely not that, but let's see. Oh, rho G? Oh, I see now. I think that's it. Okay. And so, taking into consideration that with the equation we're viewing now, the G sub mu nu is going to be an actual component, which I can actually just write it in. It's going to be the 0, 0 component. I must have forgot to write it earlier. I did. So I'll make the correction now really quickly. But it's the 0, 0 component of our covariant metric. And so, this now reduces to being, again, we basically get all the same constants, except now that particular component of the covariant metric is basically just going to be equal to -1. So this becomes oh, wait a second. Is that right? Oh, no, that's right, that's right. I see where I made another mistake. This is a negative rho. It's a negative rho. Forgot to put that there. So a negative rho, the G sub 0, 0 is also just basically -1 in this case. So -1. Let's go ahead and type that out. For a second there, I was like, wait, this isn't coming out right, but it's because I'm leaving signs off. I mean, it's very easy to forget a sign here. And so, all in all, it reduces to being, inside the parentheses, that is, negatives cancel out. You're basically going to have a positive 1/2 rho. Okay. I think that this is going to be good. I can get rid of those parentheses really quick. All right. So from here, all that's left now is to solve for what the left-hand side of the equation is going to be. And so to do this, again, we solved for r sub 0, 0 earlier. Let me take a moment and look at some of the comments, because I'm pretty sure I've just been missing comments here. I've just been talking. Dave? Who's this guy named Dave? Okay. I know some of you guys by your actual names. Maybe I'm just missing something here. Hey, Hanny. Welcome to today's stream. Oh, hello, metaphysicist. Let's see. All right, let me continue though. I'm gonna try my best to keep up with chat. All right, so from here we have r sub 0, 0. We have its equation. We can now go ahead and we can plug in what the left-hand side of the equation is going to be. But before doing so, we can now use the concept that for r sub 0, 0, and I kind of stated this earlier that I was going to talk about this a little bit. So I'm going to scroll up here on my trying to think, maybe it might be best for me to explain it using this particular form of r sub 0, 0. All right. So what we basically have here is the simplified form of the 0, 0 component of the Reciept curvature tensor. And the key things I want to note is that this first term we're seeing here, this negative 1/2 times the quantity, where these are all second order partial differential equations of the 0, 0 component of our perturbation matrix. And so that's a second order partial differential equation. However, everything else that comes after it are first order partial differential equations, but they're to the second, well, I don't want to say they're to the second power, but they're non-linear. So they're not to the first, we're basically multiplying two linear partial differential equations, making them non-linear. And so the key thing here is that given the fact that H, like all the terms of our perturbation matrix H, are small, that is, they're much, much less than 1, we can actually kind of use this idea that their partial derivatives also, that is, their first order partial differential equations will also be small as well. And so when we end up multiplying a small thing, that is a thing that's less than 1 already, but really less, like really, really small, less than 1, well, wow, my words are not coming out right. When we take something that's very small, that is when it's very close to 0, and we multiply it by itself, that only makes it even more smaller. And so what we can do is we can actually use this idea that because of the fact that we're now multiplying terms that are small by themselves, then they become even smaller. We can almost consider them to be negligible. And so the r sub 0, 0 term actually just ends up reducing to just being the very first term we're seeing on the right-hand side here, which is going to be the a combination of second-order partial differential equations. And so what I'm going to end up doing is I'm just going to copy and paste that portion, which is the 1/2 or negative 1/2 times the second order partial differential equations. And I'm just going to copy and paste that in for the left-hand side of this equation down below. So that goes there and equals, and we can keep our right-hand side. So scrolling back down, this is now what our equation has reduced to. And as you kind of even see there, I was going to talk about linearized gravity, but I didn't want to make this more complicated. I mean, I think this is the best way of explaining it. I can get rid of this. All right. And so I'm going to go ahead and typeset this. And so there's one key thing I want us to note here, that everything in the parentheses on the left-hand side of the equation actually has a very nice and reduced form for it. And also it's an actual mathematical concept. This is this is known as the Laplacian, in this case of a function where the function is h sub 0, 0. So it's the Laplacian of the h sub 0, 0 component of our perturbation matrix. And so I'm going to rewrite this as this. So I can do this. I'll maintain my negative 1/2. And so this now becomes an abla squared h sub 0, 0 and equals everything on the right hand side of the equation. Of course, the 1/2s cancel out, so I can get rid of the 1/2s. And I can bring my negative sign over as well. I don't want to. I'll bring it over to the right hand side of the equation. And so it actually turns out that this form is essentially the it essentially is Newton's gravity, but just stated in a different way. So what I'm going to do is I'm going to now pull up some online resources and we can kind of make some comparisons. Oh wait, sorry. Hey Larry, let me see what you got here. So, ignoring the heat and radiation effect of a white dwarf or a neutron star. Hey Adam. I think we end up talking about the fact that I'm trying to recall the equation in my head really quickly. You know what? I'm definitely going to go ahead and answer that question. Wait, that was the original question? So you didn't ask the question about... Okay, 1 minute. Let me quickly answer this question though, and then I'll finish up what I was saying here. So let's see. And guys, really all I'm doing right now is I'm pulling up the equation. Some of the equations I can keep in my head, but there's just so many equations to try to remember. Let's see. Black. Oh, I think this is it. So, Larry, to answer your question, the equations we derived were specifically for black holes a few streams ago. Trying to think of a way of being able to quickly modify the equation to account for the object being either a white dwarf or a neutron star. Well, I can actually still use this. All right, so negative 2 gm, where the capital M is going to be the mass of our white dwarf or neutron star. I guess it really, I mean, to be very honest though, it's going to really be dependent upon exactly what is the structural integrity of your spaceship, your spacecraft. And so what you'd want to do, I mean, I can't answer the question straight off bat. But what you'd want to do is you'd want to determine, well, what is the differential force or the tidal force you're getting from the star compared to what is it? Either the stress or strain required to actually break apart the shuttle. But at the very least, you could probably use the approximation that we derived some streams ago to be able to determine exactly what we'd expect to what sort of tidal force we'd expect across the ship. I kind of wish I could just copy and paste equations into the chat, but I don't think I can do that actually. So actually, I'm going to quickly, I'm going to go over time here, but that's okay because I want to be able to answer the question, especially if this was the original question. Um, let's do this. So I'm going to add another window. PDF2. And we're going to bring up what I have here. Let's see. All right. So the equation we derived, and the one that's going to be applicable for what you're asking, is this one right. Oh wow, it's highlighting them all now. Let's see. This one right here is what we're going to want to look at, where our tidal force is going to be basically what the left hand side of the equation is stating. It's going to be equal to negative 2gm, where m in this case, the capital M, would be the mass of our star, our dead star. The lowercase m is going to be the mass of our space shuttle. Delta R is going to be the physical length of our space shuttle radially compared to the star. And R cubed is, or the capital R in the denominator is going to represent the distance, I guess, between the center of our star to the center of our space shuttle, or basically just the radius of the star. And so what you'd want to do is you'd probably want to calculate what this value is first, assuming of course some values for m, the capital and lowercase m, the physical length of your space shuttle, and the average length of either a neutron or star or a white dwarf. And I guess you'd want to compare it to, well, what is the amount of force? And I know it's either the stress or strain that will be required to be able to break apart your space shuttle. Honestly, I'm trying to remember. One of them has units and one of them is unitless. That is stress or strain. I think it's it might be strain maybe. That has units of force. But yeah, I think it would highly be dependent upon what exactly your shuttle, what's the material your shuttle's made of. Let's see, stress, physics. But just to quickly answer this though. So strain is unitless, but stress has units of pressure. So I would imagine you probably could take the surface area. Well, or maybe you'd want to take the cross sectional area actually and apply a force to it. But yeah, that's how you probably want to be able to approach this problem. Determine what the stress of the space shuttle is, and then make comparisons between that and the equation I just showed you for the tidal force. Can we assume the main structure is iron? Can you get spaghettification from either a neutron star or a white dwarf? Um, I think again, I mean, this would still be, we'd still want to apply the exact same equation. Um, I think in the past we used the idea of spaghettification for, like, if you place a human nearby, and of course you'd have to ignore heat and radiation, right? Because that we wouldn't be able to get close enough if we didn't ignore that stuff. So so I guess in order to answer that question, I would need to be able to actually have some physical values for what the mass, or what the average mass of, for example, with a white dwarf, the average mass of a white dwarf in its typical size is. But yeah, I would imagine this, to get back to the initial question you just asked. I would imagine, um, yes, astronomy. Oh, well, actually, I don't know. Susie, is that the case? Is astronomy cast in about an hour? I know that in the past I've said astronomy cast is in an hour, and it turned out that it wasn't. I'm sorry. Am I interrupting the Star Trek show? Okay. Well, I'm gonna go ahead and finish up here. Um, I think I've said about what I wanted to say, at least for the let's see, for this particular problem. Basically, I was just gonna show that this is equivalent to Poisson's. Basically, I was gonna show that you can be able to take this form and relate it to Newton's form of gravity, and end up seeing what the h sub 0 component must be equal to, and stuff like that. But all right, guys. I hope you guys enjoyed discussing this. Let's see. No, where's my? 'Cause I had some fun. I definitely had some fun talking about it. And all right, well, I will see you guys next week. I'll be back on Wednesday, 12 p.m. Central Time. And I'll see you then, guys. All right, bye.